This is Monterey Bay Academy of Games, also known as MBAG, and the project title is Rogue Dreams, by me, Brian Barry, Jackie Luke, Roberto Palacios, and Tyler Pruitt. The problem that this project aims to solve is that mature game projects are not accessible to students. MBAG has initiated this project to bridge this gap for CSUMB students specifically. The objective here is that we give students applied skills, projects that they can work on, and hands-on experience in the process.
There are a few changes from our original plan, mostly in our improving our NPC pathfinding, changing our sound system up to be more complex, and changing our map generation from initially generating our entire map to just generating one smaller 8x8 room at a time.
Currently, we've integrated our main systems into the demo. We've also improved upon them and made them expandable. All we need to do is replace the assets that we have.
The AMBAC team's approach to this project was such that we relied heavily on the Unity ecosystem that is already in place. We wanted students mostly to focus on novel algorithm production, experiential learning, which is learning through creation of their own custom systems, and we wanted to allow students to have access to professional workflows. That's why Unity provides the rendering backbone, and students mostly provide their own custom systems.
So for our team contributions, the two things I worked on were wave function collapse and the sound system design. For wave function collapse, we made sure to have a efficient integration of this. With the diagram here, we can see that it runs around n squared, kind of between O of n squared and O of n cubed, which does fall in superlinear time complexity. Now, is this implementation scalable? It is to a point. It's definitely efficient enough for the purpose of use that we have, but there would never really be a use case of generating a 1000 by 1000 grid, for example. And for us, we're just doing 8x8 grids. It runs totally fine enough there. Now, was this a correct choice for us? It definitely was. Given that we were integrating it with a dual grid system, this worked very well on top of that, and it provided everything that we needed to feed that dual grid system. For the sound system design, initially we were going to go with Fmod, which is a third-party software. It was a little bit overcomplicated and had additional features that we did not need to use. The custom sound system does pull pretty much what Fmod has, minus those extra things that were not necessary. And it is scalable to an extent. Any built system inside of Unity will have limitations, but for the use case that we have, this is perfect for us.
I worked on two sections, the UI and the dual grid system. For the UI, I focused on adding the title, adding a background image to it, and updating the button layout. I also updated the pause menu in terms of the design and making sure that only some of the settings were displayed at a time instead of all of them. A typical tile set would normally require about 47 to 48 tiles. With the dual grid system, we can cut that down to 16. We have a couple of examples right here. The example for the dual grid is a test sample that we used for this project when implementing the algorithm. Even with the dual grid system, having multiple types of terrain such as grass, dirt, water, pathways, any other forms of tiles massively increases how many tiles you need. We initially expected to use 6 terrain types, and mathematically, that turned out to needing approximately 17,000 tiles, even with a reduced number due to the dual grid system.
So 17,000 tiles was an unimaginable number of tiles for both our system and for any artist to make, so we needed to streamline that. And to do that, we came up with a tiling system that used Burnside's lemma to calculate the minimum number of interactions each tile has with every other tile in our system. And by doing that, we can actually take individual tiles and have them do double duty by rotating and reflecting them, such that one tile is essentially 4 or more. And we also made it such that our lookups for each tile are based on the tile types. Here you can kind of see some of the drawbacks to this system. Tiles that were originally planned to be drawn only from the top-down perspective usually work quite well. They blend seamlessly with the system, but anything that had any kind of directional shadows needed to be adjusted. Otherwise, it was very clear that the original tile had been split and rotated or reflected. Now, aside from that, I also came up with a item system that was essentially ended up being a database system. And Unity doesn't have any kind of built-in database features in and of itself. There are some plugins that possibly could have worked, but we decided to do this on our own just because that is kind of the essence of what we do. To do this, first we had to come up with a custom data type. And alongside that, we also came up with a special serializable format for that data type, and all this contributed to a system which gave us O1 lookups for essentially this database, which is above average for other similar systems. And here you can kind of get an idea for how the system works. Again, the core of this is the packed item data schema, which is 2 blocks of 64 bits, but that kind of joins together in a packed item table that then both stores that information for individual items and also syncs that information with the proper descriptions and the sprites.
So Unity's current pathfinding system doesn't scale very well as instances increase or as agents increase. In my current system, I use bitboards as the representation of grids, which is just a single unsigned long integer, 64 bits. And it also scales very well as our agents increase in this system. Not only that, by using bitboards and bit operations, that allows us for more functionality beyond just defining the grid or defining population for enemies. By staying closer to hardware, that also allows our operations to be much faster so that we can do a lot more within our given restraints. I've implemented a benchmarking system between my current system, which is a form of potential field pathfinding, and A-star, and it is shown to be faster than A-star as rooms or agents increase in most situations. The only limitation being it's an 8x8 board. I've also improved the NPC intelligence such that they are more coordinated as they move towards the target, and I've also made this system very portable and modular such that I can also stick it and plug and play in any other systems. What results is a cheap and efficient multi-agent single target pathfinding system where it goes from a single U-long being transited into game space, and then from there that representation of the grid can be used in a multitude of ways. In this current situation, I'm using it as a flood fill, or I'm using a BFS flood fill such that I have distances from a certain target. So any number of agents only work off of a single instance of data of distance from the target. Overall, we want to thank Drew Klinkenbeard, Graham Devine, Sophie Jocelyn, and Eva Calzada for helping us with this project. Thank you.